In the previous video, we've discovered that there are some cases where the derivative of a complex function seems to be depending on the direction of approach, and that's obviously not desired. So what we're trying to do in this video is figuring out some conditions that will guarantee that that's not the case, that the derivative is well defined. Now, we're not going to start by looking at the full picture. We're going to start by deriving some necessary conditions for this to be the case. So if it's the case that the derivative is completely independent of direction of approach, that will necessarily also mean that if we only focus on two well-chosen directions of approach, that these two should give the same result. So that's what we're going to do here. We're going to look at a vertical approach where delta x is equal to 0. And we're also going to look at a horizontal approach where delta y is equal to 0. Now, if the derivative is well defined and does not depend on the direction of approach, then the result from this calculation and the result from that calculation should be the same. So this will allow us to define a necessary condition. And later on, we will worry about sufficient conditions. So let's start our calculation by first looking at, let's say, the horizontal derivative. So let's look at the case where delta y is equal to 0. And pause the video and try and calculate the derivative for yourself. So the derivative again is this delta f divided by delta z. And what I suggest you do is you split f in its real and imaginary parts u and v, and do the same for z, splitting it up into x and y. So pause the video, split this quantity up in components, and see what the result of the calculation of the derivative is. So what we need to consider is the limit of delta z going towards 0 of our differential quotient, which is delta f divided by delta z. Or, splitting this up in components, limit of delta z going towards 0 of delta u plus j delta v dividing by delta x plus j delta y. Now, luckily, we're in a special case here. This delta y is equal to 0, so we can just get rid of this delta y here. Now, what we then have is also, well, the limit delta z going to 0 will be the same as the limit of delta x going towards 0. So if you look at this first term here, delta u divided by delta x in the limits of delta x going towards 0, well, we know what that is. That's the partial derivative of u with respect to x, by definition. And then for the second term, we will have j and then the partial derivative of v with respect to x. So this is the result that we get when we consider this particular direction of approach. Now pause the video and try to do a similar calculation, but this time for this particular direction of approach, and see what you end up with then in that particular case. Okay, let's repeat the same procedure, but this time for delta x equal to 0. So in that case, the limit of delta z going towards 0 of delta f divided by delta z will be a limit of, well, now it will be delta y going towards 0 because delta x is equal to 0. And then we have delta u plus j delta v, and this time delta x is equal to 0. And here we have j delta y. Now, let's have a look again at the first factor here. So if we divide by j, that's going to be equal to multiplication with minus j. But then the limit of delta u divided by delta y of delta y going towards 0 is again a partial derivative of u with respect to y. And for the second term, j cancels here, numerator and denominator, and we have the partial derivative of v with respect to y. Okay, Let's now pause the video and very trivially come up with some necessary conditions for the derivative to exist. So in case we want that this result is the same as that result, so these are two complex numbers, then obviously we should have that the real parts are the same and also the imaginary parts are the same. So if we look at the real parts, we will see that we need to have that du dx is equal to dv dy. And if you look at the imaginary part, we should have that dv dx is equal to minus du dy. So these are necessary conditions that will guarantee, well, necessary conditions for the fact that our function should have a derivative which is independent of direction of approach. These conditions are very important and they're called the Cauchy-Riemann conditions, named after two famous mathematicians. And they guarantee that a function has a well-defined derivative. A different way of saying that a function satisfies the Cauchy-Riemann conditions is saying that the function is analytic. Or you might also hear the term holomorphic being kicked around. So a holomorphic function or an analytic function is a function which satisfies the Cauchy-Riemann conditions, which guarantee that the function has a well-defined derivative. Strictly speaking, we haven't really showed that if a function satisfies these conditions, then the derivative is independent of direction of approach. That's something we will do in the next video. The only thing we've shown here is that if a function has a derivative which does not depend on direction of approach, then the Cauchy-Riemann conditions are fulfilled, relating these equalities of derivatives here. Obviously, implicitly, what we also need here is that these derivatives are well defined. So this means that we're dealing with nice functions which are continuous, which do not have any singularities or ill-defined points. So this is also another condition that needs to be fulfilled, but that's implicit in what we've been doing here.